Hi, welcome back to Reader. And we are in chapters, honestly, like 4 through 6 in fluid mechanics. Also, you're going to see this in incompressible flow, chapter 5. And if you've been digging into this, you've now done some problems, conservation of mass, conservation of momentum, and likely not any conservation of energy other than maybe playing with the Bernoulli equation. And so what I want to do today is sort of one last sort of sweep through these equations. I'm going to derive the temperature equation, which is important, and then we'll sort of use that as an excuse to then switch back into the world of pure thermodynamics. And so this one's kind of fun. This is why, again, you can see the power again of the index notation. That just makes all of this significantly easier. And so if I write the conservation of momentum, and I'm going to write the differential form. So we have already sort of gone through how you go from the integral form, Stokes' theorem, to get all as a volumetric integral, which that should be true for every d volume out there. So that's how you get the differential form. And so the conservation of momentum or continuity equation is the time rate change of density plus the gradient of del J of the density uj, and that's equal to 0. And remember, this is true for both incompressible as well as compressible fluids, right? This is completely true. And then conservation of momentum is rho time rate of change ui dt. And so this will be a vector equation. So I is going to be the free index, which means this is a vector. And then we have a uj del j ui. And then that's equal to negative del I P, so the gradient of the pressure. I will go ahead and write this one as the incompressible version, just such that we can kind of stick with U, and I'll use del squared UI. I do like using this form as opposed to a del J, but just because this is nice simple form. Okay, and then conservation of energy, I'm going to write down just a little bit lower, and you'll see why. And remember that this one is then rho time rate of change of energy. Now, the energy is actually the total thing, so I'll use E here for the internal energy, plus uj over 2, so that's the kinetic energy, plus gz, right? And then actually just gi, sort of gravity there. Actually no, it'll require z. That's the potential energy. And then we have a rho uj del j, and then here I'm not going to use the enthalpy. I will go ahead and stick it as E plus PV. That would be enthalpy. You'll see why here in a second. Plus uj over 2 plus gz. Okay, and that is equal to Q naught minus dCV, and then I'm also going to put in here shear. Now, when we're playing in thermodynamics, usually we're going to ignore shear, right? Actually, you're almost always going to treat thermodynamically that friction is 0, and then you'll just do some calculations where you might estimate the friction and decide how much entropy you lost. But I'm going to keep this here as shear here for a second, because what I want to get to is actually the temperature equation. And so right now we have a conservation of energy, and then that's the full thing, right? The conservation of energy is a conservation law. There's no such thing called the conservation of temperature. But I want to show you the sort of the temperature equation, the temperature differential equation, and that's going to happen by taking this full equation here, and I'm going to dot it with the velocity. So UI. So that means now UI, so you have sums over j's, right, that are implied. Now you have an implied sum over I. And so what's going to happen with that? Well, I'm going to bring, on this term, I'm going to go ahead and bring the ui inside. And so that would be rho time rate of change, that's time, and that would be ui over 2. Right? If you will, it's velocity squared, and then the 2 will come down and cancel out. Same thing here, plus rho uj del j ui over 2, and then minus ui, and again, I'm going to write this interestingly. I'm going to say rho del I PV. Again, it's incompressible, so I'm allowed to do that. I'm allowed to pull the kind of the velocity past the density. This, by the way, this derivation gets a little trickier if it is compressible. There are a few more terms you have to handle, but I'm going to show you just a nice form. Okay, and then this is the shear one. And so remember this one, you could remember this equation as del J tau ij, if you will. And so this could also be seen as, when I'm dotting the u into it, you can see this as ui del j tau ij. You could also remember that this is also del j of mu sij if it's incompressible. And so same thing here, you could actually see this as mu ui del j sij. A couple different ways of writing it that are all basically equivalent. And so then what's going to happen here, and I'll just do the sort of the final form, and I'm not going to write it as this one. I'm actually going to keep it as this top one, such that it is a ui del j tau ij. Because honestly, what that term is shear. This is actually our shear work term, which is this one. Okay? And so the story is going to be repeated everywhere. In fact, but maybe I better stick to a color that'll really show up. How's blue doing these days? Was blue showing up well? No, not so much. All right, I'll stick to my orange green. All right, so this one, this term is this term. Now, let's see what other terms match up. And so there was a minus here. If I bring this to the side, this rho ui del I PV, well, again, this is a sum over I, which is literally the same thing over here as a sum over j. If you imply, I can switch them if I wanted to. So this term is this term right here. Great. This term is this term right here. Oh, fantastic. Okay. And then this term is this term right here. That's great. Now let's do this whole thing where we then also ignore gravity, because, you know, why not? We don't want to talk about any change in potential energy. So this would be true in a flow where you don't have big gravitational swings. So where natural convection is not a big, massive deal. You can come back and add a model for natural convection as needed. And so what you're left with then, what happened to my green? There's my green. What you're then left with, and the final step, I'll kind of write it over here, is remember that E is equal to CVT. And we've talked about that a few times. That's coefficient times temperature. Okay? So that's specific heat coefficient. So rewriting all of that, we'll put a line down here. What we then have is rho, and assuming the coefficient of heat is constant, d temperature dt, plus rho CV uj del j t is equal to, now this term is going to have two things that can happen to it. If you actually go and look at conduction, right? So you would say that, you know, if you go back to the surface integral, there's surface integral k, and then gradient of temperature the area, right? This would be the flux going across an area. And it's the same kind of thing. When you convert that, then you would get del J of K del J T, and assuming that d volume, assuming that thermal conductivity is the same, you then end up with K Nobel squared T. Okay, and so then this is equal to K Nobel squared T, and then any work left in the control volume. Well, let's just ignore it for now. Let's just pretend that there's no, I don't have a big shaft sitting there in my problem. Now, one other thing, so that was sort of conduction. There's another piece here, and this is viscous heating. And I'm going to include it here simply because, a lot of what we do here at Venus is hypersonic flight. This is actually a term you can't ignore when you start flying fast. For most of the times, you would ignore it. And so that if you include this, right, and the way to think of it is viscosity. If you look up here momentum, what viscosity is doing right here is it's sort of smothering out any curvature, right? This is going to kill the curvature, kind of smother things out. From an energy point of view, if viscosity is smothering things out, it has to go somewhere, like that energy, right? So once we've dotted it, you can see that energy is sitting here. It has to go somewhere. And so the energy actually shows up as a viscous heating, and it's usually just written as Sij, where we've sort of defined Sij before. As a reminder, Sij was del I uj plus del j ui. It was a symmetric tensor. Okay, so when you end up having here, and I know I kind of wrote right where my face is. I'll stand on my toes so you can kind of hear the punchline. This is your temperature equation. Now, we wouldn't call it a conservation of temperature. This is just the differential equation for heat. Okay? Sometimes you may consider this a scalar transport equation, because honestly, if you have some sort of scalar in there, some sort of I put a red dye in there. Like honestly, anything you do with a scalar is going to have a time rate of change term. It's going to have a sort of a convection term, and may have a diffusion term, right? That red dye is going to spread out based on some sort of gradient based on the concentration of redness. You may not necessarily have this sort of heating term, but honestly, this is a very standard sort of scalar term that you may see a lot. Okay, and so this is kind of the final, really final important thing. When you get into, say, combustion physics, I don't know that we're going to get into a lot of this quite a bit. Certainly, you can add back in here into Q. You can add like, hey, there's been some sort of combustion reaction. What else is? We'll say combustion reactions are going to show back up here in the temperature equation. If you were thinking about this from a modeling point of view, the number of equations you may have to track in combustion physics can get quite extreme. So I've seen things as simple as a two-equation model that sort of represent, not burnt and then tracking that, and then having that sort of Q come back in here and add to temperature. There's also combustion physics equations that run 2,000 lines of extra equations, and so that can be pretty gnarly, and the time steps associated with that can be pretty gnarly. So this kind of completes, if you will, the fundamental differential equation side of fluid mechanics. I will come back here. We're going to go back into the world of thermodynamics. I will come back here at some point to kind of talk through simulation experiments, because honestly, these differential equations can get quite nasty, can get quite hard to solve directly, and so a lot of this then leads towards modeling. And why it's important? Ultimately, as engineers, we are solving real problems. We want to be modeling real things, and so while this is an equation, as an engineer, we can't just sort of stop and say, well, that's complicated, I'm not going to deal with that. No, this is the fundamental physics behind the thing you're studying. Okay. And so I will talk about how you would go into modeling, the terms that we then sort of try to wash away to make things tractable, and kind of walk through what's easy computation, what's heavier computation, and then what makes this sort of challenging. And I'll be honest, this is why it's hard. This is why flows over cars are hard. This is why flows over aircrafts are hard. There's a whole world of challenges. Flows in nuclear reactors are hard because you get to different temperatures with natural convection. You can transition to turbulence. Right? All of this can get really, really hard. And so there's a value in experiments. There's values in computation. And honestly, while I'm teaching a class on thermal fluids, what I'm not actually going to get into in this book club is a class in heat transfer. Right? And the reason is very simple. Heat transfer at its simplest form is right here. Right? This is conduction. And it's really easy. And so if you're going to go take a class in heat transfer, you can 100% go in there and learn conduction very, very quickly. Radiation, if I were to write it down, radiation involves things like temperature of the fourth and radiating it away. That becomes a little bit harder. You now actually have to talk about like what surfaces can see what other surfaces, right? It's a little bit of, dealing through photons and things like that. It's very different. And so if you're involved in radiation heat transfer, you need to know about it, you need to get into it. And honestly, the final piece of heat transfer is convection. And you can say, well, really it's just solving this term with convection. Yeah, you can say that. But ultimately, because this whole thing becomes, whether it's laminar flow, then it transitions to turbulence, convection, if you've taken a heat transfer class or when you take a heat transfer class, what you're really going to see is your convection part of heat transfer just turns into a whole bunch of correlations. And do you know the correlations? Can you use the correlations? Do you know when the correlations break down? And so I don't want to minimize the role of heat transfer, right? I spent a long time doing gas turbine heat transfer. It's actually very, very, very complex. But I think more from an analysis point of view, there's only so much you can get into sort of with equations, with sort of carrying that analysis before you're just in the world of taking correlations and doing some brute force, or you're putting into a simulation doing a brute force, or you're running an experiment doing a brute force. So not to minimize it, but that's why I'm not including it in part of this sort of fundamental thermal fluids portion. And so that's it, honestly, for this portion of fluid mechanics. We'll come back in later to fluid mechanics. We'll actually come back in and get into compressible flows. That'll be a very important difference. Here I've really kind of focused on incompressible flows. But for the moment now, we sort of have the full picture, and I want to return back into the world of thermodynamics to get into cycles and things like that. But now that you've seen the full thermal portion, you've actually seen some graduate statistical mechanics where hopefully entropy makes more sense. That's going to make that portion of thermodynamics hopefully richer, make a lot more sense, and be less confusing. Right? Remember, I was teaching thermodynamics, I'd always find the students who would get kind of confused with the assumptions, with the different things. And so that's why I'm excited to sort of teach it to you this way. And so, dear readers, be reading the book, be digging in. Again, this is the point of this book club, is I'm just kind of hitting the wave tops. It's on you to go dig through the books. They're phenomenal books. And we'll see you next time on Book Club. And remember, if you're liking this, like and subscribe.